All right, let's do this. So today we get to learn about circular motion. All right. The first chunk of this is going to be totally review from what we did in honors. And then we got to add on a new thing, which is totally manageable. All right. So here we go. Oops, try again, wrong button. There we go, try again. All right, so last year when we did this, we learned about what is called uniform circular motion. All right, uniform circular motion is motion in which your object is traveling in a circular path at a constant speed. They're not speeding up, they're not slowing down. All right, but remember, we learned that even if you're going at a constant speed, because your direction is always changing, that means your velocity is always changing. And as a result, your object is still accelerating, okay? And it turns out that, I don't even want to mess with this, all right? Let's see. So because your direction is always changing, the object is always accelerating, all right? And what we learned last year was this, that like if you envision your circular path, okay, at any given instant, your object's velocity is what we called tangent to the circular path. All right, we even sometimes called it tangential velocity. Let's write that out. Tangential velocity, right? And so the idea is if the object wasn't accelerating, then it would keep going this way forever. All right, and so to prevent that from happening, to keep it going in a circle, there must be an acceleration vector that sort of points towards the circle to keep the object moving in the circular path. All right, so there's my acceleration vector. It points towards the center of the circle. At this instant, it actually points towards the center of the circle that way. Okay, and that is what is called centripetal acceleration. Centripetal acceleration. All right. And honestly, I think I talked about this a little bit in honors. I really kind of dislike the word centripetal. Sometimes you will see this called radial acceleration, okay, which I honestly like better. I wish they used this word more. And the reason that it's called radial acceleration is because it points along the radius of the circle, okay? So this drawing right here is actually, I like this drawing because it hits a lot of bases. It shows the direction of all three vectors that we care about. So let me get rid of this blue guy here. There we go. Okay, cool. So you can see here in yellow, our accelerate or our radius vector, right, points from the center of the circle out to the point where the object is. You can see your velocity vector. The velocity vector will always be tangent to the circle if you're moving in a circular path. In fact, we learned that in, I don't know, 2 videos ago, right? That the velocity vector is always tangent to the path. All right, and then your acceleration vector, centripetal acceleration, radial acceleration, points back in towards the radius, okay? Please notice this is a right angle here. So your velocity vector is perpendicular to both the acceleration and the radius vector. Okay. So even though the object is not speeding up or slowing down, it is still undergoing centripetal acceleration or radial acceleration. And that radial / centripetal acceleration is responsible for the change in direction as your object navigates its circular path. All right. So let's see, I think we hit everything here. Sorry, I had my armpit in the camera there. Let's see, velocity is always tangent to the path. Acceleration vector points towards the center. This is all centripetal acceleration that we're talking about here, okay? So I think I already talked about this. The acceleration due to the changing direction of an object in a circular path is called centripetal acceleration. The word centripetal, I guess the Greek roots of it means center seeking, okay? It's directed radially inward in towards the center of the circle. All right, so this space here is all intended for me to give you some equations. So how do you calculate centripetal acceleration? So it turns out centripetal acceleration is calculated by taking the magnitude of the velocity squared and dividing it by the radius. Please notice this equation only gives us the size of the centripetal acceleration. The direction is inwards towards the center of the circle in the opposite direction of the radius vector. Okay. If you are genuinely curious about where this equation comes from, I'm happy to show you in class. It comes from some geometry, and 99% of you don't care. But if you want to see the derivation for that equation, I'm happy to show you. All right. Now, a couple other terms that we need to know. Period. So remember, period is the amount of time that it takes for your object to complete one circular path. Okay, it's the time it takes. And it turns out if your speed is constant, then that speed can be calculated by doing 2 pi r divided by, remember, capital T is period. Okay. Once again, this equation just gives us the magnitude of the velocity, i.e. the speed. Okay. Cool. And then remember, frequency is the number of circular paths you make per unit time. What we learned last year is that your period and frequency are reciprocals. Okay. And therefore you can also calculate the velocity by doing 2 pi r times the frequency. Okay. So these are a couple equations from honors physics that you should know. They are not on your AP physics sheet. Okay. Actually, I think this guy is, but those two velocity equations are not. All three of these equations just give you the magnitude. Okay. They do not give you the direction. All right. So your centripetal acceleration, opposite direction of the radius, inward toward the center. Your velocity is always tangent to the circular path. Okay. So, boop, boop. We already talked about the direction of the vectors, I think. Cool. Let's see. All right, so let's do this example here. So it says an object moves at a constant speed along a circular path in a horizontal XY plane. So let's draw our little XY plane here, X, Y. It is going in a circular path with the center at the origin. When the object is at X equals -2, the velocity is -4j meters per second. So let's, our radius there is, what is that? -2i meters, right? So that's this when it's at X equals -2. And then it tells us that, at that instant, the velocity is -4j meters per second. V equals -4j meters per second. Okay. And so now it wants us to give the velocity and the acceleration when we're at y equals 2. So the fact that the center is here, and it tells us that it passes through this red dot over here at -2. So that looks to me like my circular path has to go this way. What is that? Counterclockwise, right? Okay, that's the only way it would be moving down when it gets through that red dot there, right? So that means that when it does get to this point up here, sorry, I keep having to move this little thingy. When it gets to this purple dot up here, what we know is the velocity vector is going to point this way, right? That way, right? It's at a constant speed. So that means the velocity is 4 meters a second, but in the -i direction, right? Okay. And our acceleration is constant. It hasn't sped up at all. So our acceleration is still v squared over r. I guess we have to calculate that, don't we? So that's going to be 4 meters per second. Notice I'm not interested in the direction at all. Squared divided by my radius. So that's going to give me 16 squared over, or sorry, 4 squared is 16 over 2 is 8. You can check the units. They do turn out to be meters per second squared. And it's directed towards the center of the circle. So that's going to be down. So that's going to be a -j. Okay. So there is your centripetal acceleration at that point. Okay. Cool. All right, so that's all I'm going to say about uniform circular motion. This is stuff we did in honors. There's not a ton to it. As long as you know the direction of those vectors and how to calculate centripetal acceleration, you're in pretty good shape. Now, the question is, what happens if the object is not speeding up? I'm sorry, if the object is speeding up or slowing down? What if it's not a constant speed? Okay, then we get what we would, I guess, call non-uniform motion, right? And so what ends up happening then is you actually have two types of acceleration. You're going to have the acceleration responsible for the change in speed, for speeding up or slowing down, and the acceleration responsible for the change in velocity. Okay, so let's do a quick example of that. Maybe before we do an example, let's talk about it. All right. So suppose we've got an object going in a circular path. Okay, and maybe right here, two things are happening. All right. So let's suppose that it's speeding up. All right. I'm going to do the speeding up acceleration vector in green. So if it's speeding up, oh, sorry. Let's say that it's going around, what is that again? Counterclockwise, right? So I can go ahead and draw in my velocity vector. So here's my velocity vector. I'm going to label that V. I'm going to put a T on there just to emphasize that that velocity vector is tangent to the circular path. All right. Now, if it is speeding up, then we're going to have what we call tangential acceleration. I did not give myself enough room to draw all this. Let me make this a little bit smaller. Whoop, whoop. All right, so if it is speeding up or slowing down, then we have what is called tangential acceleration. Tangential acceleration. And it is called tangential acceleration because the tangential acceleration vector is tangent to the circle, just like the velocity. All right. Now, if the object is speeding up, then the acceleration vector points in the same direction as the velocity. If it's slowing down, it's going to point in the opposite direction. All right. So let's assume that it is speeding up. All right. If it is speeding up, that means we're going to have an acceleration vector that points in the same direction as the velocity. That is called tangential acceleration. Okay. Now, it's also going in a circle, which means it's also got to change direction, right? And so there's also going to be centripetal acceleration. And that is going to point inwards towards the center of the circle. All right. So this is interesting. So one of the things that is, if I haven't talked about this yet, is going to become increasingly important moving forwards in this class is we have to consider our axes choices. All right. So often we use X and Y axes. Okay. Notice that's a acceptable choice of axes because they are perpendicular. All right. When you've got an object on an inclined plane, we don't use X and Y. We use parallel and perpendicular axes, right? And again, those are perpendicular to one another, so that's a good choice of axes. All right. When you've got an object undergoing non-uniform circular motion, when you have an object undergoing non-uniform circular motion, then your choice of axes is going to be centripetal, tangential. So you're going to have a centripetal axis and a tangential axis. Oops, that was meant to be a T. All right. Sometimes people will call them a perpendicular axis and a parallel axis. Okay. The idea is the parallel axis is parallel to the velocity. The perpendicular axis is perpendicular to the velocity. All right. I don't care which you use. There unfortunately isn't sort of a standard, within the physics community. I tend to find moving forward, honestly, that I use perpendicular and parallel a lot. I think for the purposes of this video, because we're just starting, I'm going to stick with using a centripetal axis and a tangential axis. Okay. So my object here is experiencing two types of acceleration. There's the green tangential acceleration and the blue centripetal acceleration. So to find the overall acceleration, now you're putting together two components, right? So you're going to have your tangential acceleration, your centripetal acceleration. Here's your right angle. So this would be your actual overall acceleration. Okay, so you would do Pythagorean theorem and you could describe the direction. All right. Now, this is kind of a convoluted example because the velocity is at a weird angle, right? The velocity is going this way, which means your acceleration is, at a weird angle. So this example that I've got over here on the other screen is probably a better example of that. All right, so let's run through this example over here. All right, so we've got a toy car on a circular track with a radius of 0.75 meters. So let's go ahead and draw our track. All right, let's go and draw. Yep. All right. So the problem tells us that the radius is 0.75 meters. All right. Let's see. It begins at rest. I'm wishing that I'd written this problem a little bit differently. Let's suppose that it begins at rest at point A. I'm going to go ahead and put point A right here. All right. So there's point A. It's going to begin at rest there. Okay. So the velocity at point A, i.e. our initial velocity, is 0. All right. And then it speeds up at a rate of 0.3 meters per second squared. So that's telling us our tangential acceleration is 0.30 meters per second squared. Remember, this is the rate at which it speeds up or gains velocity, right? Or loses, I guess, but in this case, it's positive, right? And so the question wants to know, what is the acceleration after half of a lap? So when it gets over here to point B, it wants to know what is the acceleration. And so a lot of you are probably thinking, well, you just gave me the acceleration, 0.3 meters per second squared. But you got to be careful. That 0.3 meters per second squared is the rate at which it's gaining speed, but it doesn't take into account the fact that it's also changing direction. Okay. So when we do get over here to point B, our velocity vector is going to be this way. Velocity vector is that way, tangent to the circle. And at that instant, we're going to have a tangential acceleration. But we're also going to have a centripetal acceleration, right? Responsible for the changing direction. Okay. And our overall acceleration is going to be the vector sum of those two values, the tangential and centripetal acceleration. Okay. So let's see, to find our centripetal acceleration, oh, it's v squared over r. So I need to find the velocity at point B. That's what we need to figure out, is what is the velocity at point B? Well, let's see, what do we know? We know that we started at rest. We know how quickly we're gaining speed. The problem also tells us that we're going to go half of a lap. So I can find, and again, this is another thing where there isn't really notation for this, but I can figure out what my displacement is moving tangent to the circle. In other words, what distance do I travel while I'm gaining speed, right? So that's going to be half of the circumference. So 2 pi r, that's the circumference of the circle, but I'm only going halfway around. Okay. So my displacement, if I calculate it, turns out to be a number that I've written on this piece of paper, 2.36 meters. Okay. So I know my displacement tangentially. I know my acceleration tangentially. I know my initial velocity tangentially, and I'm looking for my final velocity. So now we got to dig back into some of our kinematics equations. I'm going to use this guy, 2a delta x equals vf squared minus vi squared. Okay, and notice everything that I'm measuring there is measured tangent to the circle. Okay, so plug in all of your numbers. You know everything here except for your VF. Solve for the VF, and it turns out to be 1.19 meters per second. Okay, so that's the velocity that I have at point B, 1.19 meters per second. I guess you could put in negative j, right? Because it's moving downward. So now we can find our centripetal acceleration at that point. Well, at that point, the velocity is 1.19. Don't forget to square it and divide it by your radius. Multiply that out, and it gives you 1.88 meters per second squared. So that's my centripetal acceleration. So let me make a new drawing here. I don't love this one that I have over here on the screen, just because my vectors were kind of the wrong size. So here's my circular path. When I get to right here, what I've just discovered is that my centripetal acceleration is 1.88 meters per second squared. And we already knew the tangential acceleration was 0.3 meters per second squared. So now I can do vector addition and figure out the actual overall acceleration. So we're going to have 1.88 inward, 0.3 downwards. So here's my overall acceleration. So do the Pythagorean theorem to figure this out, and you get 1.8. Oh, sorry. 1.91 meters per second squared at, do a little bit of trig and find this angle here. It turns out to be 9 degrees. And what would that be? South of east, I guess. Or I suppose if you wanted to, you could write it in unit vector notation. And then it would be 1.88 I minus 0.3 J meters per second squared. So either this or this would be acceptable for your acceleration. All right. This is a thing that's going to happen more and more, especially when we get to, well, circular motion. Anytime you have non-uniform circular motion, you've got an object moving in a circular path and speeding up or slowing down, you're going to have these two axes where you've got a tangential axis and a centripetal axis. Notice if the object had been slowing down, pretty much everything would be the same, except your tangential acceleration would point against the velocity. Okay. I think that's everything for that one. Pretty painless, I think. Did I get everything? Yeah, that's another example from a previous rendition of this video, so you can ignore that. That's it. All right, cool.